So sorry for this. So I would like to present you work by inspired and energy efficient convex model predictive control for a quadruped robot. So speaking about quadruped robot, this is very highly nonlinear system. So if you take into account nonlinear dynamics of each actuators and legs, so it will be impossible to compute it in real time. Speaking about model predictive control. So for this, there should be done some simplifications. And so this corresponds to the real world, like almost entire weight of a quadruped robot, such as mini cheetah and unitary A1. So the entire weight concentrated in the base of the robot. So we may not consider the masses of the legs. So this is one simplification. And so this is the floating base model, if we not consider the legs and all the mass in the base of the robot, like a rigid model. And we can linearize it with in our simplification, so the robot don't move. So the angles such as roll and pitch can change due to movements, and only speaking about angular changes, only angle around z-axis can change. So with this simplification, we can describe linear system of floating base model. This is not the best model. This is not the accurate model, of course, but for the model for MPC, it can be expressed as this, and with such with empirical results, with stable control can be reached with this. So we have a linear system. Matrices A and B depend on only your angle and foot positions from the center of mass of robot. So with this linear system, there can be formulated model predictive control, convex model predictive control, with cost function is on the slide, like euros of reference of actual state and the reference states, and we should minimize the control inputs. And control inputs could be expressed as a force, ground forces of each leg. So, and as we can see, there are some equality constraints and inequality constraints. Speaking about equality constraints, this is actually a linear dynamics of a floating base model. And speaking about nonlinear inequalities, with C matrix. So this is the constraints on the ground forces, parameter friction parameter constant, and matrix D is the represented as the gate of the robot. So it's okay, it can work, it's stable, but speaking about working, it's okay. But when a robot is running, with this controller, Convex MPC stabilizes the robot Z, the height of the robot. So reference Z is constant and the velocity of Z is 0. But when we see the real animals, they don't stabilize the height. They move like smoother than the real robot. And actually, there are a lot of works about how animals in the real world move. And there is a very popular and very well-known pattern like spring-loaded inverted pendulum sleep model that can describe the movement of when animals are running. Like if we have a treadmill and located some person on, so some person running on the treadmill, and we measure the ground forces that the person generated on the floor. So there can be like they have the form as on the right top picture. So there are two lines, like a black one and a red one. So black line presented the measurement of real ground forces of person, and the red one is the sleep model. Sleep model forces. And as you can see, it's very very similar, and it can be expressed as a simple model, sleep model, when the person or animal is running. So why don't we generate sleep trajectory for the convex MPC? Why do we need stabilize on the Z, on vertical direction? So with decoupled sleep trajectory, we can reach the running of a robot 15% more energy efficiently when without sleep model. So on this slide you can see prong gait, like very simple gait when robot is running. All the four legs like move as one leg, and it can be presented as a one sleep model as one leg. And cost of transport lower by 15% when without sleep model, and peak forces lower by 2 newtons on one leg. And speaking about future work, where this task, like generating decoupled sleep trajectory as a convex MPC, again, like to design another MPC, which is more, which has higher level of trajectory generation, so it can be hierarchical MPC. And another task is about stability. Like I don't like this simplified linear model, so there are no cross product of angle dynamics, and this is not good. So I think there will be a good result if we linearize it more accurate. So thank you for your attention. I would like to answer your questions.
Thank you for the presentation. Any questions from the audience?
Can you explain me why you want to have the same behavior for the artificial dog as the real one? Because they have a different degrees of freedom, and the behavior natural for real dog it's will be unnatural for the dog with the less degrees of freedom.
But okay, I got the question. Thank you. But speaking about degrees of freedom. Actually, of course, animals like dogs have more degrees of freedom, but in general, we can catch the key feature of movements and try to make the robot move like animal, and maybe it can be it can have better behavior, and it's not proved, but this is like this, because of course the real animal and the robot are not the same. Don't have the same construction, don't have the same like in real animal they have muscles, not the actuators, okay, electrical actuators. But if we try to make it similar to this, maybe we can have some improvement.
Okay, thank you. Another question?
So if I can ask, did you find in your practice, episodes where
I didn't hear your question.
Yeah, sorry. This I think
maybe he can mute. No, he should mute.
Yeah, he should mute.
Can you please mute?
Yeah.
Okay, now you can probably hear me. Sorry, it's technical issues. So what I wanted to ask is, did you see in your practice the influence of the friction coefficient on the types of, walking patterns that you were able to implement? As in, like, we always put friction coefficient in constraints of our equations, somehow in the planar settings in the MPC. But those friction coefficients are usually, like estimates, often rough estimates, etc. Did you find a practically meaningful constraining power of friction in your work so far?
Thank you for your question. So, speaking about friction, cone friction, so this is actually the key feature of the MPC. Like they can say that LQR with constraint is MPC, convex MPC. So this is the key feature of convex MPC with inequality constraints, and they're really important because with these constraints we can constrain the inputs, like the ground force that can generate the leg of a robot. Of course, we can get the 1000 Newton meter the torque of the actuator. Of course, there are some limitations, and this inequality with symmetrics it limitate the solution, so the robot can generate trajectory for the actuators not that extreme, and with this we can have stable behavior of the robot. And speaking about friction, parameter friction, so actually this is simplification too, because firstly it was not parameter friction, it was cone friction, like leg so that for the robot leg, there should be generated some control inputs for some torques from the actuators that leg don't slip from the floor. So this is the this friction coefficient is very important, and this is empirical. It's empirically received this friction coefficient, and then it's, as far as I remember, is 0.6 with friction coefficient, and if we would like to control robot on not on the normal floor, like maybe on the glass or maybe on the ice, there would be another friction coefficient, of course. So
thank you for the answer. So, in the interest of time, we'll continue with the third paper. So the third paper is titled Grover Binary Search for Discrete Quantum Optimization, Ayaz, Baykov, and Stanislav Protasov from Innopolis.
And also the first team. Yeah, we're still working on it.
They're still not done.
That's the point. Yes. You can do it here. So, thank you for my colleagues. I'd like to tell you about our research, which we're doing with Professor Protasov throughout the year now. And it is about Grover binary search, which we called it for discrete optimization problems. It all started with this Airbus quantum computing challenge, where we had a task where a company wanted to know how they can maximize the profit by maximizing useful payload of the single flight. And mathematically speaking, it's just some variation of well-known knapsack problem with its additional constraints. But we wanted to keep the task as simple as possible. I'll explain later. So in our case, we just wanted to know which subset of containers gives the maximum mass, while it doesn't exceed the total limit in weight of the plane. So Airbus wanted to get solutions that involve quantum computing, because obviously those kind of tasks generally are not solvable using classical approach, because in such cases we had to go through each possible variant, and with each additional item the number of variants grows exponentially. But at the same time, quantum computing has proved that it has special tools to make this search much faster. And one of the main, I'd say, tools for that is Grover's quantum search. It operates on such searching problems by taking, let's say, it doesn't depend on the function itself, which we are trying to search, but on it implements search process itself, I'd say. For example, in this problem of Airbus, we know the function, which is the total weight of containers that we took into the plane. And we will try to make search on this function, just putting some different states as an input. I'm not going to dive into details on how this Grover search works, but the only point you need to know is that it has this probabilistic nature. At first, it sets every possible state to be equally probable, and then step by step, it will maximize the probability to get correct answer. And after square root of n operations, where n is the number of states, the probability to get correct answer will be maximum. It may also be 1, but it is not guaranteed, but will be maximum. So we have such powerful tool. How can we use it to solve optimization problem? The traditional approach for this is to, first of all, make some estimation of the answer, and then step by step try to improve it by using Grover search, where the function to check will be that the function of the value of the function will be bigger than current estimated answer. So when we keep repeating this process, and when the Grover search fail to find new update, we just stop and return the answer. After some reflections and experiments with this, let's say, a well-known approach, we found some concerning points. First of all, you may look at this example with these 6 containers, and let's say limit of total weight was 16. If at some point we had estimated answer to be 12, then this function to check with this Grover search is values that bigger than 12 and less than 16. And there are 4 possible answers, and what we will get is chosen randomly, depending on this distribution. Of course, we would like to get immediately 16, which is ground truth answer, but we can get unlucky and we can get 13. So we will have to repeat the process, and then again we can get unlucky, and 14, and so on. And in such cases, our time to work in terms of applications of Grover search is linear, and we wanted to get rid of it and get the guarantee of logarithmic scale. So we decided to keep same iterative manner, but rather than raw increment of the answer, we decided to look at this range. So the same example, we know that our first estimated answer is 12, and then the ground truth answer lies somewhere in this range from 12 to 16. And we decided to try to just split this range in half and run the Grover search with that will look for the answer that bigger than the median value. So if we find any answer from the second half of this range, then it means that we go to the second half and we just halved our initial range. So you see, in this case, if we found values bigger than 14, then the new range of the answer will be from 14 then 16. If we fail to do so, we go to the first part. Either way, at each step, we will decrease the length of the range by half, which guarantees us logarithmic scale. So a few words about how to encode this problem and encode this function to get the total mass of the containers. First of all, it is needed for our Grover search because it needs to apply this Oracle function in the quantum computer to get the correct answer, and it also has to be set in superposition, the values of the function. So we used already well-studied techniques. First of all, we used quantum Fourier transform addition method to add the constants, which is just the masses of the containers in our case, to the register of qubits. And we had to use controlled version of them to entangle like the answer of the value of the function with the state that we put into the function. So the program which we pass into the Grover search looks following. First of all, we count what mass gives us some state. Then we make comparisons, also using same addition and subtraction methods. Here, first of all, we compare with the current estimated answer, or the median in the case of binary search, and the maximum allowed weight. So after we designed such function, we can proceed with experiments which will compare our Grover binary search with this traditional adaptive search. So this fact that we are guaranteeing logarithmic number of applications of Grover search, we thought that it will give us like better speed. So we will need much less calls to the quantum computer to run the Grover search. But in fact, this test, which we provided on a simulator, showed that we were wrong. And in fact, they both, adaptive and binary search, keep the logarithmic scale, but our approach is slower by some constant, multiplied to some constant. And after some reflections, we found out that this happens because when we run adaptive search, if we fail to update at any step, it can be because we found the correct answer, but also it can be just because we were unlucky. Again, Grover search is a probabilistic algorithm. It will just stop and return the answer. But in Grover binary search, in either ways, we are just halving the range, and we have to keep going until the length of the range will not be equal to 1. So this fact alone makes our algorithm a bit slower, although it coincides with our theoretical predictions that it will give a logarithmic scale. But at the same time, we also decided to measure how good the answers are provided of both algorithms. We decided to look how often does algorithms show the ground truth answer, and when it just makes some approximation of it. And we found out that on average, our algorithm tends to return correct solution more often than the adaptive one. And that happens also because of the same fact that we lost in the speed competition, because gas can fail at any step because of the probabilistic nature of Grover search and just stop. But in the binary search, it can fix itself later. For example, if we didn't find an improvement which was there, and we moved to the first half, at some step further, we can get new value which was bigger than the range we are in, and we can understand that at some step before we made a mistake and go further. So for that reason, we were better at finding correct solutions. So we decided to make a more experiments in that direction, and we made a synthetic test, which is a bit unfair to our adaptive search. This has so-called a plateau where each new value is bigger exactly by 1 from the previous, and those kind of tests are harder for adaptive because at each step it can fail, and again we can fix that problems with binary search. So in such experiment, success rate for our algorithm was 91% against only 5 for traditional one. But if we interested only in some approximation, for both of them, the mistake wasn't greater than 10%. So this gives us some summary that those both algorithms should be used for different purposes, and when different aspects are more important. For example, if it is speed, which is crucial to our task, then we use adaptive, or if we can wait a bit longer, but we just need a more precise answer, then we can use our proposed binary search. Thank you for your attention. I'll be glad to answer your questions.
Yes, waiting for this.
My basic question is that when you presented the specific case in which Grover binary search performs better, yeah. So it's a synthetic case, yes, where you have a plateau. Can you give at least an idea of where these kind of problems may appear when there are a lot of suboptimal solutions, like very similar to an optimal one, which are like multiple, so that's why GAST can stop progressing while GBS can work much better.
Let me think a bit. I think actually in any such of optimization tasks with the growth of items in our set, we will get more and more also, yeah, I think in these cases it can be any optimization problem where we have those items are looking very similar, then they will produce very similar results. For example, I think logistic problems. We have a lot of roads in the map, which are similar in terms of the length of them, and the total length of the path which we choose from city A to city B, they differ only a bit if we swap some paths in the middle of the roads in the middle of the path, and those kind of cases also produce these plateaus, which are better to be solved with our binary search. I hope I answered your question.
Oh, thank you. So sounds like with the growth of the problem, in general, your advantage will become bigger and bigger.
Yes.
Okay.
Let's start with number 6.
Which?
Number 6.
Number 6. Ah, 12. Okay.
Honestly, I completely cannot understand that. You already have seen how gas may be poorly when probability of accident is probability of so you have number of campaigns.
Yeah.
To low Ayaz. So what that really means that one campaign solution is the same probability as for example 10 campaigns.
No, it's
So we need to clarify.
yeah. In such case, we consider not like each container individually, but the state, let's say, where we decided to took those containers, like subset from the set of every container, and we mark it as a state and describe the probability that this state, like those containers which we took, is the correct one. So we don't look at the containers individually.
Yes, I mean that maybe I can comment. So imagine you have the some constraints put on the problem, and there are some solutions which are in our particular case. The search space is the power set. So we have a set of items. So our search space is the power set. So all possible subsets. So when Ayaz means the probability of a solution, it means that there is equal number of subsets satisfying some value. For example, as it's on the graph, can you show the next one? So there is a range of solutions which are satisfying the constraints, which are giving you the answer 13, 14, 15, and 16. Let's say dollars, which is like the estimation of the problem. And there is, for example, 274 such solutions for 13, 315 for 13, and so on and so on and so on. So if they are distributed uniformly, then when you try with the particular algorithm, Grover algorithm, sample a solution from a given constraint, you will sample them uniformly, meaning that you will choose one of those with the same probability. It can be not uniform, meaning that there's one solution with 13, two solutions with 14, and 100 with 15. Then you will most probably sample 15.
So some comments about that our problem set wasn't that deep because now we are somehow bound with this technology our age, let's say. Because first of all, the real quantum hardware which are open for us, they would only work with the 7 or 8 qubits, which is extremely small. And I don't know, run the problem with 2 or 3 containers only. So we use simulators, but then again, they don't give a lot of options for us because, first of all, mathematically, we already cannot simulate quantum computers with more than 50 qubits. And on my computer, I could only manage to run with 25. So we had to make tests this small. Yes.
So one quick question from me. So when you compare the speed of the two algorithms, right?
Sorry.
Here, what if your algorithm, you stop it prematurely at the average time that the adaptive algorithm stops? You understand? So you do not wait in order to find the optimal solution. It takes too long. You stop it.
Yeah.
You compute what's the average time that it takes for the adaptive algorithm, and you stop it there. Then how far will you be from the optimal solution? This is how you normalize with time, and then see how far you are from the optimal solution.
You want my thoughts initial about that? What will happen?
What will happen? Because it seems that your algorithm finds
Yeah.
the optimal solution right at the end, at least from the CDM.
Yeah, because it has to find it right at the end because we are working until the length of the range will not be equal to 1. This is like our condition to stop. But I know you are proposing to stop if we fail to find an improvement, which means that the answer is not in the right half of the range where possible answer lies. But we still didn't find any answer. We are just working with the ranges.
Let me answer this question. So I think it's in compute. So we can find the gap between the averages. It's around, like, let's say 5 launches. 5 launches mean that, like, as we know, now we've been trying different times. Means that there are 2 steps of iterative algorithm, which is binary search. 2 steps of binary search means 1 multiplied by 2, and then again by 2. So at most 4 values, like dollars, rounds, or whatever, robots.
And that will be exactly the result which gives us adaptation.
Yeah.
Okay, thank you. Then we turn this off.
Yeah, just stop sharing. Yeah, yeah.
Okay, now we go back to paper number 1 on the stability of the system of Thomson vortex, n-gon, and a moving circular cylinder.
Yes. Thank you. My name is Leonid Kurakin. I present our research with Irina Ostrovskaya on the stability of the system of Thomson vortex n-gon and the moving circular cylinder. Next slide, please. The dynamics of the interaction of point vortices with a moving cylinder has been studied in many papers. The motion equation of such a system are constructed in paper 1, Borisov, Mamayev, Ramadanov. The papers 2 and 3 give a overview of the current state of the field of research, together with the original results of the authors. Next slide, please. The motion of a circular cylinder interacting with n identical point vortices is considered. The equation of motion are obtained by Borisov, Mamayev, Ramadanov. Here, Zc, Zk is complex variables. Xk, Yk are Cartesian coordinates of vortex. Xc, Yc are coordinates of cylinder center. V
is cylinder velocity. R is radius of cylinder. A is the eddy mass of the cylinder. Gamma and gamma 0 is given by this formula, where gamma capital is circulation of the cylinder and gamma 0 is the intensity of identical point vortices. Let gamma 0 is equal to 1. Next slide, please. This system can be written in the form 2. The Hamiltonian H is given by formula 3. Next slide, please. This system has the solution 4, corresponding of the stationary rotation of n identical point vortices. Я слышу самого себя. Point vortices is located uniformly in the cycle of the radius r0. The angular velocity is given by formula 5. We study the stability problem of this solution. The stability problem has 4 parameters. 3 continuous parameters, Q from 0 to 1, A more than 0, and gamma, and discrete parameter N. Passing to limit A to infinity in the system 1, we obtain model of motion of point vortex outside fixed cylinder. Our study show that the stability problems for the cases of fixed and moving cylinders are related. In particular, for n is more than equal 4, instability in the case of a fixed cylinder implies instability for moving cylinder. Let us first present the known result on the stability of stationary rotation of a vortex polygon in the case of a fixed cylinder. We highlight the case of gamma equal n and the case of arbitrary circulation gamma. Next slide, please. The case of a fixed cylinder with circulation gamma equal n. This problem was solved by Havelock in linear formation. The instability takes place for any value of parameter q. In the case of n is more than equal 7. And in the internal q star n less q less 1, instability is 2. In nonlinear setting, this problem was solved in our papers, Kurakin Ostrovskaya, SMG and RHD. The orbital stability of stationary rotation was proved in the internal for even n 2, 4, and 6 in the internal from 0 to q star n. Next slide, please. And for n equal 3 and n equal 5 in the internal the stability orbital stability proved for 0 to q03 and for n is equal 5 from 0 to q05. For the case from q03 and q star 3 and from q05 and q star 5, all resonances up to and including the 4 order have been found and studied. There are 2 resonances that lead to instability in the nonlinear setting. It is resonance of the double zero at n is equal 3 in point Q03, and resonance 1 to 2 resonance 1 to 2 at n is equal 5 at point Q star. Next slide, please. The case of the fixed cylinder with arbitrary circulation gamma. For arbitrary values gamma, this stability problem has been considered in our papers. In particular, the resonance of double zero diagonalized case for n is equal 3 and the resonance 1 to 2 for n is equal 5 that lead to instability are studied for different values of circulation gamma. Next slide, please. And now about the case of moving cylinder. We consider first the case when circulation gamma is equal n. The stability problem has 3 parameters: Q, A, add mass of cylinder, and n. Next slide, please. The change of variables 7 lead to perturbation equation of relative motion the system 2-3 for a perturbation equation with the Hamiltonian E, given by formula 8. The stationary solution 4 corresponds to continuous family of equilibria C. The stability of the continuous family of equilibria 9 is equivalent to the orbital stability of the stationary solution 4. And orbital stability in our problem is stability of the equilibrium family C. Next slide, please. The linearization matrix L of the system with Hamiltonian 8 about the zero solution has the form given this formula. Here, symmetric matrices F1n, F2n, and skew-symmetric matrix G0n are circulant matrices. Next slide, please. The characteristic polynomials of linearization matrix L is given by equality 11. Here, the polynomial phi1 is biquadratic or bicubic polynomial, depending on the parameter A. And polynomial phi gn are biquadratic or quadratic polynomials. These polynomials do not depend on A. These polynomials coincide with polynomials written by Havelock in the case of a fixed cylinder. Thus, the analysis of the eigenvalues of the linearization matrix L has been reduced to a study of the roots of polynomial psi1 and the application of the Havelock results for psi g from more than 2. It is analytical results. And the criteria, and now the results. This analysis, the criteria of linear, we have the criteria of linear stability in the case of moving cylinder for gamma equal n. In the case n is more than equal 7, our solution is unstable for all of values of problem parameter. Instead of parameter a, we will consider the parameter alpha, given by formula this formula. For case in the case when n is more or equal to and less or equals 6. In this case, analysis of eigenvalues of matrices L show that the space of parameters Q alpha where is divided into two types of areas. White area is linear stability area and shaded area is instability area. Next, please. Slide, please. Fig 1. The diagram of stability of stationary rotation of Thomson vortex n-gon around moving cylinder in the case n equal 2. We have two white area of linear stability and shaded area of instability. The value alpha minus 1 correspond to fixed cylinder. The alpha minus 1 is fixed cylinder. The curves alpha 1, 2 correspond to multiplier roots of polynomial psi1, and the curves alpha 2 is the zero root of the polynomials psi1. We have analytical formula for these curves. Next, please. The diagram of stability in the case n is equal 3. We have two white area of linear stability. In this case, 2. Alpha is from -1 to -0.8, and this alpha is from 0.9 to 1. We have this two domain of linear stability. Next, please. And the diagram of stability in the case n is equal 4, 5, and 6. A for n is equal 4 point, B 5 point, and C 6 point. We see when Q is more than Q star n is unstable. We have unstable. Next, please. The results of alpha minus 1 correspond to Havelock results in the case of fixed cylinder. And the constant in figures Q star n was calculated by Havelock. This is this constant. Next, please. Thank you for the attention. And sorry for my poor English and problem with presentation.
Thank you very much, Professor. Questions from the audience? One question.
When you say about non-linear equations and instability for Hamiltonian system, what we mean and what kind of instability appears in your system with respect to Hamiltonian approach.
Sorry, please reply.
When you say about instability in non-linear case, you say
non-linear, yes.
Non-linear case, and you say about Hamiltonian equations, and that means that you have some integral of motion. That means that your instability solution actions or moving through some cover on the parametric space. What kind of instability you
Stability? We have only linear stability, and the problem of nonlinear stability is the big work what we must do. Now we only work linear stability.
But for nonlinear case, we have, if you consider its linear limit, then such trajectory may be stable in general. It's only some short period of instability which we see on your research.
Sorry for my English. Может кто-нибудь сказать по-русски мне вопрос? Я плохо улавливаю.
Когда мы исследуем нелинейные случаи, да, там на самом деле, конечно, мы линеаризуем, и в линейном случае бывает так, что линейная задача действительно неустойчива. Ну, например, если мы рассмотрим математический маятник, линеаризуем в окрестности нуля и добавим там вот эти вот
клетка, да, клетка.
Оно окажется, что она с линейной точки зрения неустойчива. Но на самом деле, если мы посмотрим исходную нелинейную задачу, то оказывается, что она устойчива в главном, а неустойчивость это возникает из-за того, что мы отбрасываем члены при линеаризации. И примерно
сейчас я понимаю.
Или же вот такой случай, когда, например, твердое тело и неустойчивость в случае волчка Эйлера, например. Там есть устойчивые решения, а есть одно неустойчивое. Там действительно вот как бы, ну, есть...
Сейчас, извини, сейчас я понял. Вопрос содержательно интересный. Спасибо за него. Можно сначала отвечу по-русски, а потом, если можно, значит, постараюсь по-английски сказать. Но ситуация такая. Когда вы говорите про то, что вот, значит, осцилляторы, то это в линейном приближении клетка, Жорданова клетка. Вот когда сейчас слова неустойчивости, которые мы произносим, это случай, когда собственное значение имеет вещественную положительную часть, то есть экспоненциальный рост. И в этом случае нелинейные слагаемые, согласно Липунову, не могут погасить неустойчивость в линейном приближении. Вот. И поэтому вот все эти ответы, которые у нас выписаны, это именно то, что, собственно, экспоненциальная неустойчивость в линейном приближении. Клетки, которые возникают, резонансы, они возникали, вот и нами исследовалось там вот среди всех резонансов, которые были в случае закрепленного вихря, закрепленного цилиндра, там был двукратно ноль диагонализируемый случай, но была двукратная пара чистомнимых Жорданова клетка. И там аккуратно использовалась теория резонансов, и с учетом нормализации слагаемых до 4-го порядка включительно в точной постановке эта задача была решена именно с учетом слагаемых 4-й степени, устойчивость или неустойчивость. Это была большая работа отдельная вот по резонансам. В данном случае, в данной нашей работе, в данной сейчас работе, о которой я рассказал, это была первая часть, то, что проделал Хавилок, она и связана с тем, что мы нашли ситуации, вот это, когда все собственные значения лежат в левой полуплоскости. Есть собственное значение с положительной вещественной частью, экспоненциальный рост в линейном приближении. То, что касается вот этих белых областей, то здесь, конечно, только работа только начинается, стрижка только началась. Это будет отдельно. Задача рассыпается на серию содержательных задач, будут и такие вот клетки. Но в данном случае, да. Я ответил. Да, спасибо за вопрос, спасибо.
Thank you very much.
Sorry for my poor English and problem with presentation.
No problem. Everything is sorted out now. So we go to the paper. We go to the fourth paper, preliminary study exploring GitHub repository metrics. Will it be present online?
Yes, I will present.
Okay, please start.
Can you see my screen?
Yes, everything is visible. You can start.
Okay. My name is Guzel Safiullina, and today I will present our project in exploring GitHub repository metrics. Today we will start with introduction and its review. After we will move to methodology part. After we'll go to results, discussion, and finish with future directions. Now we move to introduction. There are now many teams which are working on open source software development, and open source project might be different in scale. They might be projects only of one person or the whole team. And GitHub is the largest web service which based on Git, where developers of different projects can interact. And now GitHub has more than 83 million developers, and number of projects exceeds 200 million. So GitHub is a source of that data about projects. And for us, it's important to understand how metrics which characterize repository affect quality of code, its popularity, and which insights we can get from data. Our paper contains qualitative and quantitative study of GitHub repository metrics. And the main purpose is to establish relationship between metrics of project, study distribution of data, and get possible insights. Now move to methodology part. We start our proposed approach presented on this scheme. We start with data extraction and pre-processing. After we do exploratory data analysis, distribution tests, correlational analysis, and clustering. We will discuss each step in details. First, data extraction and pre-processing. Our dataset includes information about GitHub repositories. The data which used in paper is retrieved with GitHub repository statistics API. And data frame contains more than 18 metrics, which contains information about commits, contributors, forks, issues, repos, etc. The next step is exploratory data analysis. To visualize data, we do dimensionality reduction with PCA, and also we calculate statistics such as mean, standard deviation, median, mode, and 25% and 75% quantiles. And also we calculate confidence interval using Bootstrap. The next step is doing distribution test. we use Kolmogorov-Smirnov statistics to test data for normality. Next part is correlational analysis to find linear and non-linear dependencies between features. We calculate correlational matrices. And the next, clustering. To cluster data in different groups, we use k-mean algorithm, which minimizes the function of sum of squares of distances from each point to the center of cluster. And we use dbscan algorithm, which is based on the criterion of density of located points. Now we move to results section. We have collected data about 764 repositories and 83 metrics. After we removed duplicates and fill missing values, if number of missing values occupies less than 30%. Also, we remove metrics which contains only 0 values. And after preprocessing, we have 732 repositories and with 81 metrics. The next is exploratory data analysis. We calculated, we applied PCA and find out that 20 features contains 19% of information. And after we found that data is skewed to 0, we calculated simple statistics and find for almost all features, mean was close to 0. And for the most of features, mod was less than mean. For 66 features, mod was equals to 0. For 14, mod was equals to 1 or 2. And only for one feature, mod was equal to big number to 482. All this shows that data is skewed to 0. And one more important thing, that for all features, standard deviation was much more bigger than mean. And after that, we apply Kolmogorov-Smirnov test, and it shows that features, the data are not normally distributed. And so it means that if we calculate Pearson correlation coefficient, Pearson correlation coefficient wouldn't be normally distributed. And after we go to calculate correlational matrices, and now we go to discussion part. In this part, we compare results of calculation of Pearson and Spearman correlation, and find out that there are some pairs of features for which there is a big difference in Pearson correlation coefficient and Spearman correlation coefficient, and try to find out why. As you can see on this figure, for this pair, Pearson correlation coefficient is small, while Pearson correlation coefficient is more than 0.8. it's all because of two observations for which features are big, and if we remove, for example, this observation, when Pearson coefficient reduced by 40–50%, and after we analyze highly correlated metrics and give explanation why there is such a big correlation, which list contains 22 pairs, which are fully presented in the paper. And the last part of result is clustering. We use two algorithms, k-means, with two clusters, and we use DBSCAN algorithm, which find 58 outliers, which you can see on the screen. But all these outliers is big projects. For example, there are some projects from Azure or from Microsoft, so we can't remove them from our work. After that, we decided to calculate statistics for both cluster again separately. So we calculated statistics for one general class and for outliers, and find out that after that standard deviation became smaller or comparable with mean. And now we move to future directions. Now we can look at cluster labeling or working with received information about features. And now that's all. And thank you for your attention. If you have questions, I would like to answer.
Thank you for the presentation. One question.
Can you hear me? So thank you for your talk. I think I have a bunch of questions, but I will start, I think, with the major one. In the end, as I understand, it's not a directed research, so you were exploring what's with the data, and in the end, you decided to do some clustering with some random parameters. So can you just give me an idea how it happened that you took these two cluster methods with these parameters which you provided?
So your question is why we use k equals to 2? Do I understand correctly?
Basically, you used only two clustering algorithms to explore the data. You didn't mention whether you used it for the original dimensionality or for the reduced one. And also, you did mention why you took k equals 2 and which parameters were given to DBSCAN. So how it happened that you explored it in this setup?
Yes, for DBSCAN, I think it's better to refer to paper, but for k-means algorithm, I can explain. We try to use elbow methods to find the best k. And we can say that there is a steep descent after it, but there is some difference in the features, so we decided to use this as a hyperparameter. And we use both clustering algorithms on the full dimensionality data without dimensionality reduction. Yeah, thank you for your question.
So may I ask the additional one? So you said that you didn't reduce the dimensions, and you said that for a lot of features, basically the mode was equal to 0. So it's kind of an, I think, a good indicator that a lot of them were basically categorical features, right?
Yeah, yeah.
Yeah, or it is discrete. So how it happens that you use distance-based clustering methods to explore discrete data? I think it's not very like a suitable approach. So at least it should be one hot encoded, it should be normalized. So did you do something like this?
While preprocessing, we normalize data and using min-max scalars.
Okay, thank you. Any other questions?
One question from me. So you've explained what kind of variance you obtained, the mean, the clusters. So, but if you want to explain to a layman, right, to someone who doesn't understand what the variances mean, what will you explain to him about GitHub from all the data and all the processing that you have done? What can you say about GitHub? What kind of a database it is? What have you discovered?
Maybe the main thing that in GitHub, the most repositories in GitHub are empty, or there is no voters, or there is one participant. So the general cluster includes projects which are for study or just for for private using, which are not tend to be big projects in the future. And the number of really popular and big projects are small.
Okay, thank you. Thank you for the presentation.
Thank you for attention.
Now we move to the final paper, State Observer for Tensegrity structures.
Can try.
So
Yeah, I'm good to go. Yeah, you can start.
good evening, everyone. My name is Kirill Glinskiy, and me and Sergey Savin have conducted a research on state observer for tensegrity structures. First, we will talk about the tensegrity model itself. I will also give you a definition of state observer. We'll also discuss no distance coordinates, linearization of our system, propose an observer design, and we'll show the results of our experiments. So the tensegrity model itself is a structure which consists of rigid bodies and cables, which affected by compression and tension. Rigid bodies affected by compression, cables by tension. And this tensegrity structure can be expressed in the form of a state space. You can see it on Formula 1, where x dot is our future state, A is a state space matrix, X is our current state, B is an input matrix, and U is our control with which we can affect on our system. What's interesting is that in practical cases, we cannot retrieve the current state value directly. We need to have some measurements, outputs, and these measurements can be presented as a linear function of states, y equal to Cx, where C is an observer matrix.
However, not all systems are observable. For example, if a system is observable, it is possible to fully reconstruct the system state from its measurements. For example, when the vehicle going through a tunnel, we can collect information from sensors, and then we can reconstruct the position and velocity of the vehicle while it was in the tunnel. The problem with tensegrity is that the most common approach to represent the tensegrity structure results in non-observable system. So the most common approach is to present the tensegrity structure as a position of nodes. So the state will be presented as nodes positions. It is easy to model and simulate. It is human readable format. However, the system is not observable. We are trying to design an observer for our system. First, we need to somehow handle this issue. The key solution which we use in our paper is no distance representation. Basically, it says that we can present our state of a tensegrity structure as a difference between nodes positions. And in such format, we can find the observer, we can design an observer for our system because it is possible to estimate the absolute center of mass for this system. It also gives us a possibility to obtain a minimal representation for our system using orthogonality principles. Of course, it contains some cons. We need to perform an inverse mapping to recover nodes positions, and our dynamics will be with explicit constraints. Let's move to the system dynamics. Here on the formula 3, you may find the Newton equation for our tensegrity structure on the first row, and on the second row, you can find the dependency between two approaches, node distance and node position. D here acts as a constant mapping between two representations. And having this equation in a block matrix form, we can find delta double dot using Schur's complement and knowing the relation between Z and delta, which was shown on this slide. We can also dynamics for minimal coordinates. However, there exist some nonlinear elements here. It is a parameter f. This is elastic forces, and we want to linearize it. Easily do it because the left part, formula 5, is a constant, and we know the relation between delta and z. Thus, we can find the differentiation over delta. We can produce the system dynamics in a block form, and you can see the results on the 7th formula. Now, when we produced the system dynamics for minimal representation form, we can move to observer design. Basically, we here assume that measurements are linear with respect to position and velocity, and our design you can see on the formula 8. Also, to make everything in a state space form, we need to define a system state and observer state. We've done it using formulas 9 and 10. And we can then design a Leuenberger observer. Here, the L matrix is a gain matrix obtained from Riccati equation. The cost function can be found in research paper, and C acts as an affine component. A matrix here is the A matrix from the previous slide.
Then we conducted an experiment on X-shaped tensegrity structure with 4 nodes, and we applied a control for a state space shown on the formula 12, and obtained an estimation error norm for all 4 nodes. For complexity issues, we decided to put only norm, not all 4 nodes here. And as you can see, our state space observer in Leuenberger form converges to 0, thus our control was applied correctly, and we achieved a good observer design. Also, I would like to mention that our paper combines no distance representation and exploits orthonormal properties, and combining these things all together, we solve a very big problem because tensegrity structures are often famous for their complex dynamics, and with these two, combining these 2 approaches, we solve this issue. So I guess that's it. Thank you for your attention. I'm ready to answer your questions.
Thank you for the presentation. Questions from the audience?
Can you please comment on how was?
We've had 2 observers. We've had we have a marker here. No, I mean, like, I want to drive.
Just explain.
We've had the 2 observers. The design of the observers was pretty simple. It was just like containing of zeros and ones. And the initial error was like 0.03. And we also assumed some initial parameters like stiffness, etc. Applied this to a formula for the Leuenberger observer and obtained this result. Also, like, we've used the norm formula, which I guess is straightforward.
Can you also please go like a couple of slides there? I think one was link picture, one just maybe. So here I just make a comment. It's not a question. What I want to say is what I find interesting about this all the things that was done here is that the second point is equation 3. The second row of this matrix is just essentially constrained. You can just delete it. Take the first row, you will have normal operation of motions, it will be fine and gives standard Newtonian mechanics. In the second equation, what it does, it makes it more complicated. But then it uses like this whole system to express just deltas. Deltas get us this linear system with linear H, which is just simple to solve. So what I want to point out is that maybe the main value of this presentation is just this idea of using constraints to make symbolic expressions simpler, makes Jacobian simpler, smaller, etc. Somehow this works for if you can show the same structure, it works for quite a simple system. Otherwise, the first one. This works. Interesting. Mechanical equations just.
Okay, thank you. Other questions? If not, then I close the session. Thank you for the presentation. Alexander?
I'd like to thank everyone to come today. So we're going to close our conference. So thank you, everyone. I would like to thank the people who helps a lot with the organization of the conference. I would like to thank who did a lot of technical work to prepare this conference, during the conference, and he will do some other stuff to make the papers published later on. And Irina also helps us with the organization. So thank you, everyone, and good luck. See you. So at 7:30, so everyone who wants, welcome to the bar. So we'll just time to discuss, to meet together.